This is video 5 on expected value. We're talking about conditional expectation, and conditional expectation is somewhat um, similar to the idea of conditional probability. Now we have some new information, right? And that new information impacts probability, it changes probability. And because the idea of expectation is based on probability values, obviously the expected value will change as well, right? So we can actually compare that using this like pictorial representation of heights of people in the US, right? So here is the probability distribution function, and the expected value is somewhat 66.5 inches, right? And this is for the entire population. Now you can think about it in terms of like there are different types of subpopulation in the US. For example, a certain subpopulation will not conform to this probability distribution function that's displayed here. Um, we can assume one subdivision, for example, male versus female, right? If you look on the right hand side, we have the female and the male PDFs separated. And as you can see, the expected value of height for only females is 64 inches, and expected value of heights for only males is 69, right? So there is a significant difference between the expected values. And that's because here my expectation is conditioned on certain parameters. For example, here I'm conditioning my expectation on the fact that I'm only interested in the height of female population, or I'm interested in the probabilities of heights conditioned on being female. And this is important. Why? Because I somehow shrink my sample space and then calculate my probability on that, right? So for problems like these, we calculate something called expectation, conditional expectation, or conditional expected value, that's denoted by this, or the way you read it, expected value of x conditioned on a, right? And the way we calculate that is pretty similar to what we've been doing until now. So again, it is going to be the sum of the actual values that the random variable takes on, right? So x for all the entire sample space. Omega here is nothing but sample space s, right? So that times the probability of x equals x conditioned on a. Right, so that's the only slight difference here, right? I'm still utilizing the PDF, but this is a conditional PDF, right? And there is no difference between a conditional PDF and a normal PDF. It's also a PDF. It's just that the way we are calculating probability has changed, right? But it's still a probability distribution function. The only thing that we need to understand is that we are interested in another probability space, which is maybe smaller than the one that was the original one. Okay, so in order to demonstrate this, let's look at an example. Okay, so we are interested in if x is the sum of the roll of two dice, find the expected value of x given that die 1 is equal to 4, right? So here, instead of finding e of x, I'm interested in finding ex given a. Okay, and so the formula for that, just a quick reminder, is x for all values of x in the sample space S and x, but find the conditional probability distribution function for this particular case, right? So for our problem in specific, I can write down that I'm interested in first finding the probability, and then I'll calculate the expected value, right? So let me go and calculate this part. Probability of x, die 1 is 4. Right? From our definition of conditional probability, I know that I can calculate this by finding the probability of x for all x's, and die 1 is 4 over the total probability of die 1 being 4, and this is both are fair dice, right? So that's an assumption here. Okay, so if we quickly go back and visualize our die 1 and die 2, if you remember that, so there was like this column for 1, 2, 3, 4, 5, 6, right? Each of these outcomes here, like for example, 2 was here, 3, 4, and this is 1, 2, 3, and so on, right? Each of these outcomes is equally likely, right? So the probability value associated with each outcome is again 1 over 36, right? and we are interested in this here, right? So we are interested in 5, 6, 7, 8, 9, 10, right? So we are interested in this particular column and these set of values. So these are our x's, right? But each x has the probability value 1 over 36. And so for probability of all x's equals x and die1 equals 4 is still 1 over 36, right? So my numerator is 1 over 36. And my total probability for die1 equals 4, die1 equals 4 is just one out of those 6 outcomes, right? So the probability that die1 equals 4 is 1 over 6. So the probability of this conditional probability is 1 over 6, right? Okay, so here I have like one of the terms from my expectation equation. I also have like these values, right? All these values 5, 6, 7, 8, 9, 10 is what I need. So the expected value for x given die1 is 4 is actually 1 over 6, which is my probability, times each of these x's, right? So 5 plus 6 plus 7 plus 8 plus 9 plus 10, right? Which comes out to be 7.5 most likely. Okay, so with this I end the video on conditional expectation. In the next video I'm going to talk about law of total probability. And in fact, let me state it in this video only, and then we can go about doing some examples on that, right? So law of total, not law of total probability, by the way, law of total expectation. And this takes forward the law of total probability. So I'm not like completely wrong there. This allows us to compute a probability by considering different cases for the outcome and using conditional probability, right? So this helps us compute the expectation of a random variable when its probability is divided into certain parts, right? So to get the expectation for x, maybe it's conditioned on a and conditioned on not a, right? Is actually the sum of the expectation of x conditioned on a times the total probability of a plus the expectation of x conditioned on that's the events that are not in a times the probability, the total probability of the events that are not in a. Okay, so this looks familiar to our probability equation itself. Let's look at its application in the next video.